Okay, good morning, everyone, and welcome back. Please, before we start, as usual, do you have any questions for me? Any issues with homework? Any concerns or comments? Let me see. I see a question. Is the final optional sense to replace is well as an accurate representation of our grades? Okay, yeah. So the final is not optional. The final is not optional. In fact, the final is the most important exam because nothing replaces the final, right? Nothing replaces the final. But the final itself can replace, the score for the final can replace what? One midterm exam, you see? Yeah, but the final is irreplaceable. So yeah, and then the grade on WebAssign is an accurate representation. Yeah, all the grades are on WebAssign. Don't use Canvas because Canvas, we just input the scores for the written portion, right? Canvas is just supporting because you are not in class. We are not in class, it's online. So that's the part where I use for the Zooms, proctoring and stuff, right? But the actual grade is on WebAssign. So when you check WebAssign, that is your actual grade, right? And when you check your score on WebAssign, I've already dropped 5 homework scores. I've already dropped 3 quizzes. For the quizzes, I'll see if I can drop maybe 1 more. But I've dropped 3 quizzes. I've dropped 5 homeworks. So your grade is not going to boost any further, right? I've already dropped all those stuff. Now, the last thing I'm going to do is when I'm adjusting the score, I will replace your lowest midterm score with your final, if your final happens to be higher. Are you okay? Yeah, please, does that clear everything up? Or you have further questions on this? Are you okay? Okay. If anything comes up, please feel free to reach out, right? Feel free to reach out to me as soon as possible. Okay, now, are there any other questions before I start the lesson? Okay, then let's continue from where we left off. Right, the last time we met, we were trying to do like integration, right? Finding the area or the net area from first principles, right? That's what we were trying to do. So we looked at the question. I'm sharing my PowerPoint now on 5.2. If you can't see, do let me know. So we looked at, where is this question? Yeah, so we looked at this. So we're on example 2, part B, right? For the first part, we did the Riemann sum for right endpoints, which was just an estimate of the area or the net area. Now, this time around, it wants us to find the exact integral, right? The definite integral, right? So let's do this. So I'm going to the whiteboard. So I already wrote the question down here. So we learned that when you're trying to evaluate this exact integral, the definite integral, is going to be given by the limit of sums, right? So it's the limit as n approaches infinity of a sum I from 1 to n of. Now, for this one, for the sample points, we can choose either the left endpoints or the right endpoints or the midpoints. It doesn't matter. But when you choose the right endpoints, the calculation is easier. It's way easier when you're trying to do this limit of sums thing. So we always use the right endpoint. So that'll be f of what? S sub I, and then what? Finally, what? Delta x. So this is what you're trying to compute, right? Now, later on, we will learn rules to get this derivative, this integral, right? But for now, we are doing it from first principles, right? And I'm showing you this just so that you know how we do it from first principles. But as we saw for the differentiation, no one really does it from first principles. The first principles is just what is used to derive all the rules, and then we use the rules from there, right? So let's at least see how the first principle works, right? By trying to compute this. Though we just need to find the pieces of this, right? We need to find f of s sub I, we need to find delta x, right? And then put it in and then find the limit of the sum, right? Now, one other thing is we have to also note that s sub I is equal to what? Is the a, right? Which is the lower bound plus what? I times delta x, right? We showed this previously. So let's try and find all of these and put them in, right? So how do you find delta x? Delta x is b minus a all over n, right? So in this case, our delta x, our b is 3 and our a is 0, right? So that means that'll be 3 minus 0 all over n. So we have delta x to be what? 3 over n, right? So we have this piece. Now let's find the s sub I so that we can plug it in the f of x, right? In this case, since the function is given by the integrand is this, right? S cubed minus 6x. We have the integrand f of x equals what? S cubed minus 6x. So when we find the x sub I, we just plug it in this function, right? So let's find the s sub I, right? S sub I will be equal to what is a? Well, a is 0 from our question. So is it 0 plus what? I. What is delta x? We just found that to be 3 over n. So that's times what? 3 over n. So everything simplifies to what? 3i over n for the x sub I, right? Now that we have s sub I, let's find f of x sub I, right? Which is this piece that we need, right? To find the limit of sums. So that one will be what? We know f of x is s cubed minus 6s. We pick it from the integrand. It's just the integrand, right? So if you want f of s sub I, it's just going to be what? 3i minus n all to the what? Cube minus 6 and then what? 3i over n, right? So we have f of x sub I. So that's the final piece. Now that we have these two pieces, let's find the limit of the sum, right? Limit of that sigma, of the sum of that, and then we'll get the what? The definite integral. Please, any questions on this setup? Okay, I'm going to move on to the next slide to write it out. This is going to be a long one. Okay, so we have this 0 to 3 s cubed minus 6x dx, right? This is equal to what? It's a limit of sums. So we have the limit as n approaches infinity, and then the sum I from 1 to n, and then the f of s sub I. F of s sub I is this, right? This whole piece. So, and I have delta x to be 3 over n. So that'll give me, I have 3i over n all cubed minus 6 times, so 3i over n, and then all times the delta x, which is what? Delta x is 3 over n, right? So just put that in there. So all times 3 over n, right? And this will be like the limit of something that we saw in appendix E, the last problem that we did under appendix E, right? So trying to solve this limit, I'll say, okay, now the index of summation here is I. So that means that all n's inside this sigma notation will behave like constants, right? So the first thing I'll try and do is, let me make my life a little bit easier. Pull this 3 over n out because it's a constant. It's not dependent on the index, right? So that give me limit as n approaches infinity of 3 over n, and then the sigma I from 1 to n. For this piece, let's simplify this a bit. I have 3 cubed, so that'll be 27i cubed, and then all about n cubed. And then for this final part, I have 6 times 3i over n, that's 18i over n, right? So that's the first step, right? Now the next step is, when I have sigma, the sigma notation here, right? The capital sigma and a difference of terms, then I can just apply the sigma on each term, right? So that'll give me limit as n approaches infinity of 3 over n, and then the sigma I'm giving to each term. So I have sigma I from 1 to n of 27i cubed over n cubed, and then minus what? Sigma I from 1 to n of 18i over n, right? Please, any questions so far up to this point? Any questions up to this point? Any questions so far? Okay. Now, in this case, the index is still I, right? So this 27 over n cubed is like a constant. It doesn't depend on the index. So similar to what I did for the 3 over n, pulling out the 3 over n, I can also pull out the 27 over n cubed for this first part, right? 27 over n cubed, leaving me with I from 1 to n of I cubed. And then for this side too, the 18 over n is like a constant, right? It doesn't depend on the index and the index of summation, which is I. So I can pull that out. So I have 18 over n, and then sigma I from 1 to n of I. Now, when you get here, at this point, you realize that these are stuff we derived in appendix E. This one, this sigma of I cubed, and then this sigma of I. We derive these under appendix E, right? So under appendix E, we said this one is going to give us limit n approaches infinity, 3 over n. I have 27 over n cubed. For this piece, under appendix E, the solution for this was n plus 1 over 2 all squared, right? And then for the sum of the first n positive integers, that's Carl Friedrich Gauss, his formula. right? That's just going to be what? N plus 1 over 2, right? So like so. And then we have this, right? So to bring your mind to where I got these from, don't forget that I wrote them down. I'm going to show you. Let me, yeah. So these are what I told you about. Remember, I told you about these. So you see the sigma of I is given as this, and then for the I cube is given as, that's where I'm picking my information from, right? From the results in Appendix E. Okay, now let me go back to the whiteboard. Please, any questions up to this point? Okay, now the sigma symbols are out, right? So everything now reduces to the limit. Oh, okay, I see something. One more question. No, no problem. If we get a lower grade on our final than lowest test score, does this still replace the lowest? Okay, so if your final is lower, right, than your test scores, then your final doesn't replace any of your midterms, because your midterms are higher, right, than the final. So then the final will just be for the final only, right? The score for the final will be for the final, but for the midterm, nothing is replaced, right? The final being higher gives you like a boost, the replacement thing. So it only helps if you score higher on your final than the other midterm scores. Please, does that make sense? And feel free to ask your questions. Yeah, it's fine. Are you okay? Is it clear or no? Perfect. Okay, so then let's continue. So if there are no questions here, I'll need to move on to the next slide to wrap this up. So anybody needs time here? Okay, so we are getting limit as n approaches infinity, right? So there's a limit at infinity. So let's see. For this one, I have 3 over this. Okay, let me write it here so that I don't have to reference 27. And then one is 27. Is it 27 over n cubed? Yeah. So 27 over n cubed, and then n plus 1. Okay, n plus 1 over 2 all squared, and then minus 18 over n plus 1, 18 over n plus 1 over 2. I hope I got it right. Let me check, make sure I didn't make any errors. It looks good. Okay, so we are here, right? So let's do this limit at infinity, right? So let's do this. So I have, let me see, limit as n approaches infinity. And then for this first piece, I can distribute the 3 over n through, right? So I have 3 over n times this first piece, 27 over n cubed, times the whole bunch, n plus 1 over 2 all squared, minus 3 over n times 18 over n. And then I have times n plus 1 over 2, right? Like so. So when you get here, let me see, can anything cancel out? Oh, okay, not yet. So now let me see. For this part, I have limit as n approaches infinity. Let me try and make my life a little bit easier. 3 times 27, that's going to be 81, right? 81 over n to the power 4. And then for this side, that would be n squared times n plus 1 all squared all over 4. So this is what I have. And then for this piece, let me just leave the, oh, these 2 can cancel out and reduce it a little bit. I have 2 goes here, 1, 2 goes into 89, right? So that will reduce it a little bit. So I have 3 times 9. That's 3 times 9 is 27. So let me clear this. So I have 3, 9, 27. Okay. And then I have over n squared, and then times what? Okay, this clears, this clears. Then I have n plus 1. Right, okay, looks good. Yeah, down good, 3 on top. Yeah, everything looks okay. Now, when I get here, I'll say, okay, I have limit as n approaches infinity. To make my life easier in taking this limit, let me group the constants on one side. I have 81 over 4. Now, for this n to the power 4, what I'm going to do is I'm going to have n squared over n squared times n plus 1 all squared over n squared. And then I have minus 27 times n over n. And then I have n plus 1 over n. Right, so I'm here. Is there any questions up to this point? Right, when you get here, it's up to you. You can decide to multiply everything out and do the limit at infinity, right? But we need to simplify things as best as we can. That's why usually questions like these don't come up, because they are very long. Like from first principles, the problems, how you work it out is very, very long. So now I have limit as n approaches infinity. And then this side is 81 over 4. And then the n squared cancels n. So that just give me 1. And then for this side, I have the question is, what's the degree of the numerator? I'm looking at this piece. Can anyone help me? What's the degree of the numerator for this n plus 1 all squared all over n squared? What's the degree of the numerator? Let's use those shortcuts. Anybody? Do you still remember? I hope you remember. Yeah, the degree is 2. Perfect. Thank you. The degree is 2. What about the degree of the denominator? It's also 2, right? So that means the answer will be what? The leading coefficient, the quotient of the leading coefficient. The leading coefficient up here is 1. The leading coefficient down here is 1. So that's just 1. Minus 27. What's the degree of this numerator? The degree on, okay, the n cancels the n anyways. And then when you have n plus 1 over n, the degree of the numerator is 1. The degree of the denominator is 1. The coefficients, the leading coefficients are 1 and 1. So that's also 1. So this limit of constants will just be 81 over 4 minus 27. Yeah, we are here. And then simplifying this, let me, please, do you have questions on this? I hope it makes sense. So 4 over 4. So that's just going to give me what? So 81 minus 27. 81 is just 3. So that's 81 is 20. No, wait. Is it 27 times 3? Okay, good. So if there's 27 times 3, and then I have minus 27 times 4 over 4, then I can just factor out 27. I have negative 27 over 4. Right. Maybe let me adjust it so that it fits in here. Sorry, let me adjust this. Then I don't have to write that a small piece of answer on the next page. So 81 over 4 minus 27, right? And that's just equal to 81 over 4. 81 is 27. I don't have a calculator here, but you can do it whichever way you want it. So like so, and then minus 27 over 4, all of this over 4, right? So I can factor out 27, and then I have 3 minus 4, should be negative 27 over 4. So that's my answer. Or someone prefer to write it as negative 6.75, I think. Yeah, because it's 4 divided by 4. 4 goes into this, yeah, 6 times 20, 26. No, it goes into this 26. No, wait, 24. Yeah, 24, 6, 24. And then 24, we'll be left with remainder of 3. And that one, 3 over 4, that's 0.75. Yeah, so that's it. That's another answer in decimal form. Yeah, please, any questions here? I hope it makes sense. Oh, what happened? Yeah, so this is our answer. Anybody needs time here? Any part you don't understand? But at this one, I'm just showing you some like to test a lot on this stuff, but it's too long. The calculations are usually too long, right? So yeah, I'm just showing you that how we do it from first principles, but we are going to use the rules in the long run. So if there are no questions, then let's get back to the PowerPoint slide. Oh, anybody still needs time? Oh no. Okay. Now we are back on the PowerPoint. So this is going to give us some notes on how they found it, right? And it's basically what we just did, right? So just do that. Oh, this for the right endpoints. And then for this one, it's just showing us that because the integrand, the graph of the integrand has some part below the x-axis and some part above the x-axis, the definite integral will be a net area, not an area under a curve, but a net area, because the positive side, the definite integral will be the positive side minus the negative side, right? So the B is just the solution that we just did. And then doing this, that's a long one. They give notes on this, this, you get this. Yeah, so that's our answer. Yeah, nice. Okay. Yeah, and then as I was saying, this will be a net area, right? To be a difference in area. So it's just the positive side minus the negative side, right? And then it's just saying that if we wanted to use like approximations, rectangle approximations, or we wanted to compute Riemann sums for a larger n, right? Using right endpoints. Then for r to the n equal to 40, we get this 400 and so on, 500, 1,000 and this. So you see that when you use the approximation, it's getting close to what the actual value which we obtain. You see, as you increase the n, then it approaches the right endpoint. So it's just illustrating the idea that this is valid, right? The fact that the limit of sums is giving us this, and then when we use the numerical approach, we get something close as we get bigger and bigger value, as we take n to be bigger and bigger values. It's just illustrating that it's quite close, right? Now let's use the midpoint rule. Now for the midpoint rule, I've already talked about it briefly, but I've not actually shown you an example of how we work it out, right? So here we are just going to work it out. The midpoint rule is nothing new. It's just the Riemann sum, but the sample points are midpoints. That's all. So we use the midpoints to determine the height of the rectangle using the approximation. That's all, right? So that's what it's talking about. So for a sample point, S by star, right? We could have picked right endpoint or left endpoint, but in this case, for midpoint rule, you use midpoints as our sample points. Okay, so this is a formal definition, right? We know that we can use Riemann sums to approximate a definite integral, right? So depending on the number of rectangles you want to use, you can use the midpoints. So as you can see, if you have, say, x0, x1, x2, xn, sn sub 1, n minus 1, then you'll be using what? For this interval, you know that this interval is always the width. The width is here. The width is the same. The widths are equal. So it's always the same here, right? It's always, no, not this entire. I mean, up to S3. This one is dot, dot, dot. So let me cancel this. It's delta x right here. And then within this interval 2 is delta x. So the width is always the same. So if you want the area of the rectangle within the first interval, you know that the width is delta x. And then instead of using the left endpoint or right endpoint, you use the midpoint, right? So that's what we call, say, S bar 1, the midpoint for the first interval, right? So that'd be x0 plus x1 all over 2, the middle, right? The midpoint. And then that will give us the height. So we find f of this midpoint, and that will give us the height for the first rectangle. So that means the area of the first rectangle will be the width times what? The function evaluated at that midpoint, which will give us the height, right? So you keep doing that for all that up to the last n interval, and you get this. Since the width repeats itself, we can just factor it out, and then we have this, the sum of the heights, and that's all. But it's just talking about how it works. Let's actually see how it works in an example. But before I move on, please, you have a question here. Okay, let me solve it so that you see exactly how it works. So for this one, it says use the midpoint rule with n equal to 5 to approximate what? This definite integral. I'm going to do this on a whiteboard. I'm going to do this on a whiteboard, right? So I'm doing this on a whiteboard. So this example number 5, excuse me. Give me a sec. I don't know what's happening. Oh, that's weird. Okay, so now I'm here, right? Example 5. Oh, Karen, do you have a question? Feel free to unmute yourself and speak.
Oh, sorry, it was an accident.
Oh, that's okay. That's okay. Okay, so now let's go. So we have this definite integral. So 1 to 2, 1 over x dx, right? We are trying to use what? 5 rectangles, right? And then, so 5 rectangles. Let me partition this since I'm done with all those long stuff. This one is going to be brief. Okay, so 5 rectangles, right? So now the thing is, let's identify our A and B. Our A is 1, and then our B is what? Is 2. Right? Our A is 1, our B is 2. Okay, so we have these. So let's just find the delta x, which would be the width, right? Because you're using 5 rectangles, then the width, you know, the formula is always b minus a all over n. So in this case, it will be 2 minus 1. It will be 2 minus 1 all over n. N is 5, so 5. So that'll give us 1 over 5, or better still, 0.2. Right? Now, after getting this, let's find the interval. Right? So it's from 1 to 2. Right? So to get the next point, we add this width. Right? We add the width. So 1 plus 0.2, that gives us 1.2. Add another one, add a width again, 0.2. Because it's midpoint, let me leave some space because I'm going to do for midpoint. Okay, so let me bring it somewhere here. 1.2. The next one is 1.4. The next one is 1.6. And then the next one is 1.8. Okay, so I'm here, right? Now, if I wanted to use left endpoint or right endpoints, I can just pick the sample points from here. But in this case, we're using the midpoints, right? So you need the middle of this, the middle of that, the middle of this, the middle of that, and then the middle here. Right. So for the first piece, for the first midpoint, how do I get the point? Well, is this going to be 1 plus 1.2 all over 2? But 1 plus 1.2 is 2.2, right? And 2.2 divided by 2 is 1.1. So the midpoint here is what? 1.1. Now, you can do the same thing by adding the endpoints and dividing by 2, but that one is too tedious, right? So when you get the first point, you can just keep adding the width again, the same technique, right? So 1.1 plus 0.2, that's just going to be 1.3, and plus 0.2, 1.5, plus 0.2, 1.7, plus 0.2, 1.9. So we have the sample points, right? We have the sample points. So these are the sample points you're going to use to determine the height of the rectangles. Please, are you okay so far? Any questions? Okay. Okay, so then if there are no questions, let's do this, right? So for the midpoint, we use this symbol, we use M, right? Right endpoints, we use R, left endpoints, we use L, right? So midpoint, we are going to use the M. And then the subscript here will be 5 because you're using 5 rectangles, right? 5 rectangles. So that's just going to be equal to what? Now, for the first piece, for the first interval, my width is just going to be what? 0.2 times what? The function, the height within that first interval. And the height will be the function evaluated at what? The sample point, which is 1.1. So f of 1.1. For the second interval, right, 1.2 to 1.4, the width is still 0.2, 0.2, right? And then the function evaluated at the sample point, which will be f of what? 1.3. Right? So you get a picture now, right? So you can just keep going. So this plus 0.2 f of 1.5 plus 0.2 f of 1.7, and then plus 0.2 f of 1.9. Right, so you get these, and the pieces are 1, 2, 3, 4, 5. Nice, you're using 5 rectangles. Right, now that's why we can factor out 0.2 because it always replicates. So it's just 0.2. Now let's find the f of 1.1. Well, going back to the question, right, you see that f of x is the integrand. F of x is 1 over x. So if we have this, then f of 1.1 is just going to be 1 over 1.1. F of 1.3 is just going to be 1 over 1.3. F of 1.5 is just 1 over 1.5. F of 1.7 is just 1 over 1.7. And then F of 1.9 is just 1 over 1.9. Right, so we have this. And then the rest is just calculator work, right? So you just punch all of these in, and you get your answer of, let me look at the answer here. It's just approximately 0.69. I'm looking at the answer on the PowerPoint. So 0.69 190, let me say 1908. Yeah, so this is the value. So that'll be what? Riemann sum approximation using the what? The midpoints. Right. So this is an approximation to the, in this case, I don't know whether it's going to be net area or actual area. I think it looks like an area. Yeah. So that's it. Please, any questions here? I hope it makes sense. Okay. Is there any part you don't understand? Okay. Then let's move on. Now back on the PowerPoint. Yeah. So the PowerPoint has just these nice notes, right? So it's just this using the midpoint rule, right? So that's the key, using the midpoint rule with 5 rectangles. So approximate this. Partition, you get the midpoints for as your sample points, and then everything just follows. Get this estimate. Yeah, so this one is area under a curve because the function is strictly positive, right? It's strictly positive. Yeah, so area under a curve. Okay, now The next thing I'm going to show you is how to evaluate definite integrals using areas. Now, when we started the area problem, I told you that the reason why we do the rectangle, using the rectangle approximation is the curve may not take on the shape, the outer edge of the curve may not take on the shape of any known plane figure, like say a rectangle, a circle or something. But the thing is, if it does take on the shape of what? Of a known plane figure, then you don't necessarily have to go through this limit of sums. You can just calculate the area directly, right? By interpreting it in terms of the areas of the plane figures that we know. So for this problem, let's look at these two. How do we do that? Now for A, let me try and divide this into two pieces. So for A, right, the thing is, what's the integrand? The integrand is f of x equal to square root of 1 minus s squared. And this is just a semicircle, right? It's a semicircle with a positive part on the x-axis. So when you graph this, it's like so. So we have this, if you write this equation, what do you get? You get, let's say you have y squared plus s squared equal to 1, right? This the area of a circle with radius of 1 and center at the origin, right? So for this piece, you can have y squared equal to 1 minus s squared, and then y equal to either plus or minus square root of 1 minus s squared. So this is the equation of the semicircles, right? So since this is strictly positive, then that means you're looking at the semicircle above. So I have 0 here, right? And then the radius is 1, right? So we're looking at the semicircle. It's a positive side. It's the positive side we are considering. So you're looking at this piece, right? So this is the piece. Now, because the integrand takes on a shape of a known plane figure, it looks like a semicircle, right? When you graph it, it's like a semicircle. So because it takes on that shape, we can say, okay, let's not do limit of sums for this. We can interpret it as areas and just calculate it. So the thing is, from 0 to 1, that's where the integral is over, right? It's from 0 to 1. So from 0 to 1, you can notice that, oh, this is half of a semicircle. So we are just calculating this piece, this area. That's what the question is asking for, right? The definite integral is just an area. In this case, it's just half of a semicircle, right? So that means that this integral, instead of going through limit of sums, we can easily compute it as, and it's positive, right? It's above the x-axis. It's positive. So we can compute that as well. The area of a circle itself is pi r squared. The area of a semicircle is pi r squared over 2. And then the area of half of a semicircle is going to be what? Pi r squared over 4, right? So our r is 1. The radius here is 1. So just 1 squared. So that's just going to be pi over 4. Please, are you okay with this? Or let me explain again. The thing is, first grab the integrand. When you grab the integrand, I hope you've not forgotten this area. Sorry, the formula for equation of a circle. The equation of a circle is x minus h all squared plus y minus k all squared equal to r squared, right? In this case, since we don't have any h or k, the center is at the origin, right? And then there are two pieces of this semicircle, but we are considering the positive square root of 1 minus s squared. So that means the positive side of the semicircle, right? But the definite integral is between 0 and 1. So that's just 0 and 1. So we just need to calculate the area here. In this case, we can see it as an area that we can compute. And that's just going to be pi r squared over what? Over 4. And that's just our r is 1 under this circumstance. The 1 is the radius here. So it's just 1 squared. So that's it. We are done. Right. Now, what about B? Right. So B, we look at the integrand. The integrand is x minus 1. Right, so let's grab this. X minus 1, how does it look like? So for x minus 1, you have it at 0 here. So where are we integrating from? From 0 to 3. So it would be a good idea to see what the value is. So at 0, when x is 0, the function is negative 1. So at 0, you have negative 1. This is the point. And then when x is, say, 3, let's say 3 here, right? 3 is somewhere here. So when x is 3, the function value is 3 minus 1, which is 2. So somewhere here, let's say 2 is here, right? So like so. And then we get this, something like this. So this this is the integrand. This the integrand, right? This f of x equal to x minus 1. Now, after getting this, you say, okay, now let me see. What is this point? Well, this point is where the y is 0, right? Well, this point, this place occurs when you have x equal to 1. When x equal to 1, then this point is what? The f of x is 0, right? When x is 1, you have 1 minus 1, which is 0. So this point is 1. So now that you have this, you are trying to compute this space. It is between the curve and the y and the x-axis. So the question is, which shape does this take? Does it take on the shape of a known area, plane figure, area of a plane figure that we know? Yeah, these are all triangles, right? We have triangle here and we have a triangle down here. But then one other thing is, for the first piece, it's going to be a negative area because it's below the x-axis. And then for the second piece, it's going to be a positive area because it's above the x-axis. So it's going to be a net area, right? Let me get some more space here. Let me obtain a new Control M. And then let me do this. Okay, so we have this. Let me replicate it. So B, let's change color again. Okay, so B, we have this shape. So here, -1. And then here is 3, right? And here is 1. So it touches 1 at 0 here. Oops. The graphing is something. Okay. Okay, so let me use like trace. Yeah, that'll work. Nice. Okay, now let me trace. Yeah. Okay, this will work. Okay, and then here's 2. Right. So as I was saying, right, when you do this partition, you have an area here and you have an area there. Right. But in this case, it's going to be a net area. The definite integral was 0 to 3 of s minus 1 dx. It's going to be a net area because there's some part which is below the x-axis and some part which is above the x-axis. So let's just calculate the areas of these two and just subtract the A2 from A1, right? So with the A1, how do we get the area? Well, since it's a triangle, the area of a triangle is half base times height. So that's going to be half. What is the base? The base is from 1 to 3, right? 1 to 3. So what's the distance there? From 1 to 3 is 2, right? And then what is the height? The height is just from down here to up there, and that's 2. So 2. So that means that when you do this computation, you get 2. So that's 2. That's 2. 2 for A1. Now let's get the area for A2. Well, A2, that's also a triangle, right? It's half base times height. But this one, okay, I already have the minus here. Let me compute the positive one and just do the minus. So I have half. What is the base? Can anyone help me? What's the base? Let me see if you guys see what I'm trying to put across. What's the base here?
1.
1. Thank you. And what's the height? What's the height from here to here? I think I see something in the chat. Close, -1, close. Don't forget that we don't do, yeah. So there are 2 ways you can do this. Either you do the A2 as a negative or you compute it as a positive, but then note that in the long run, you'll be subtracting. Do you see? So -1 is still okay because in a sense, it will give us A2 equal to negative, right? It will give us a negative area, right? Which when added to A1 will subtract. But usually we don't have negative area. So we rather say, okay, let's compute it as a positive and then subtract it. That one makes more sense. You see? Yeah. So you say the height is from 0 to 1, which is 1. So that means that's half. So when you're done, you can say, oh, this is going to be a net area. This definite integral is just 2, which is the A1 minus half, right? And 2 minus half is just going to give us 3 over 2. Done. Please, I hope you understand this. So that's how you do it, right? There will be more examples. But any questions here? Okay. Then let's look at this example. Now, this looks like a much more reasonable example. It's unlikely I'm going to give you a question for you to grab the integrand, because some of these can be challenging, right? For example, this one, if you're unable to acknowledge that this a semicircle, then it's going to be tough, right? So that's the main challenge, right? But usually in your homework, I think you have this. Well, one of them has absolute value. That one you have to graph it yourself, but you also have this one in there, right? They'll graph it for you and you have to compute the area, right? So for the first piece, you can see that for this one, we don't have to do limit of sums, because I see that this piece is like a triangle from 0 to whatever this value is. Okay, let's see. This one is 12. So here is 6 and here is 3. So it's increasing by 3. Okay, so from 0 to 6, let me write these down. There's 6 and jump, and then 3, 3, 6, 18. Right, so from 0 to 6 is like a triangle. From 6 to 18 is like a semicircle. And then from 18 to 21 is also like a small triangle. Right, so now let's look at the question. So from 0 to 6, let's find the definite integral. Well, this one from 0 to 6 is just a triangle. So we're just finding this area. So that's what area of a triangle. What is that? Half base. What's the base? Can anyone help me with that? What's the base for this? Help me 6. So that it's a bit more interactive. Did someone say something? Yeah, 6. Perfect. Thank you. Yeah, so that's just 6 times the height. What's the height? Can anyone help me with this? What's the height?
12.
12. Perfect. Thank you. Yeah, so 12. And then you have it. You're done. You see, it's that straightforward. So if it's in terms of area, your work is pretty much cut out for you, right? It's going to be easy. What did I say? Not pretty much cut out. That one means it's hard. But it's just going to be easy, right? So 2 goes into 6, 3. 3 times 12 is what? 36. You're done. Next, 6 to 18. 6 to 18. Please note that this is under the x-axis, right? So what are we getting here? This definite integral. What is this piece? This is a semicircle. What's the area of a semicircle? It's pi r squared over 2, right? The area of a circle divided into 2. Okay, so now let me try and get my radius for this semicircle. The radius will just be from 12 to this point, right? What's this distance? It's 6. So that's the radius, right? The radius is 6. So if I want the area, right? Please note that this is a definite integral, right? And the piece is under the x-axis. So not to forget, let me bring my minus here already, right? And I have pi r squared. What's the r? R is 6. And don't forget this is a semicircle, so divided by 2. So that'll give me negative 36 pi over 2, right? And that's the definite integral. Oh, yeah, I can simplify this a bit. I think that's negative 18 pi. Right, I hope I've not made any errors. Yeah, looks good. Next, let's look at the C. C says find the entire thing from 0 to 21. So from 0 to 21 will be this piece, that piece, and then the last small triangle here. Right, so let me find the area of the last triangle. Right, let me say area from 18 to 21. Now that one will be a positive area, right? That will be a positive area. So, but that one's also a triangle. So that is half base. What's the base? The base is 3. And then the height is also what? It's also 3. So you're getting what? 9 over 2. So I have all the pieces I need. So it will just be this area plus that area and then minus this side. Right? That'll give me the entire area, or the net area in this case. Right? So I'm going to have 36 plus what? The small triangle here is 9 over 2, and then minus what? 18 pi, and that's it, right? So 36 over 2, I can write this as 9 over 2 is 4.5, right? So that's 40.5 minus 18 pi, and you're done. That's all. Please, I hope this makes sense. Any questions? So this one, you don't use limit of sums. Anybody needs time here? Okay. Now, let's go to the properties of the definite integral. This one is going to be like the rules and the differentiation, right? So you are building up, you're starting with the rules now. So one property is whenever you have a definite integral and you're integrating from the upper, this one concerns the limits of integration, the upper limit and the lower limit. Well, you can flip the upper and lower limit, but then when you flip it, you have to negate the definite integral, right? So this is what it's saying. So here we have integrate from b to a and then the integrand f of s dx. And then that's just going to be the negative flip. So the b will now become the upper limit, the a will come down, and then f of s dx. So an example is, suppose you have, say, 1 to 3, right, of a function f of s dx. Then that's just going to be the same as what? The negative, and then 3 to 1 of f of x dx. So that's property, the first property. Now, any questions on this? You'll be using these later on. So the next one, if your limits of integration are the same, then this is going to be 0, right? The definite integral is 0, right? So that's 2 to 2 of f of x dx. That's 0. So you don't even need to think about doing any limit of something. It's just going to be 0. Now, why is that? Now, this comes from the fact that you know that the area can be computed as limit of sums, right? So limit as n approaches infinity, sum I from 1 to n, f of s by delta x. What is delta x? The delta x for this case is just going to be b minus a, but your b and your a are the same. So you're going to get a minus a over the n, which will be 0. And 0 here will always be, it will make everything what? A sum of zeros, which is 0. And then the limit of a 0 is 0, right? So that's why we have this piece. Now, other properties. Whenever you are, for the first one, the definite integral of a constant, if the integrand is a constant, then it's the same as finding the area of a rectangle. So for this one, let me show you, right? If the integrand is a constant, then it's like this. When you graph the integrand, it's just a horizontal line. So if you are finding the area for the upper and the lower limit, so that's from A to B, then it's just like finding the what? The area of a rectangle. And so we can interpret it like how we did it for finding the definite integral by interpreting it in terms of area, right? So that's just going to be what? Area of a rectangle is what? The length times the width, right? So the length here is going to be b minus a. And then the width here is always going to be that c, right? So just c times b minus a, and you are done. Okay. Now the next one, when you have the integral symbol here of a sum of terms, then you can just do the integral of the sum of the integrals, right? So it's kind of like a integral of a sum is the sum of the integrals. The next piece is like a constant multiple rule kind of thing. Whenever you have a constant times a constant which doesn't depend on the variable here, you know that whenever you have the x here, it means the independent variable is x. Whenever you have such a case, then the constant can always be pulled out, right? So an example for 3 is, suppose I have, say, 3 times f of x dx, say 0 to 2. Then it's just going to be what? I can pull out the 3 because it doesn't depend on x, and then do 0 to 2 f of x dx, right? And then the last one is, whenever you have an integral of a difference, then it's just the difference of the integrals, right? These are the key ones, right? They'll be very important moving forward, right? Now, let me just show you some of the proofs. The proofs are already on there, but it's not really relevant. I'm not going to test you on those, but at least we have to know how we are getting these things. I've already shown you the one for the constant, right? Now, let me explain the one for the sum. Why is it a sum? Now, for this one, I don't think this is too helpful to see. A very good way to see it is using the limit of sums idea. Whenever you have a sum of terms, the integral of a sum of terms, then it's just what? The limit as n approaches infinity of the sum I from 1 to n. And then this here is just going to be what? Don't forget that kind of like f of x is a sum, right? So that would be f of s by plus g of s by. But then you know that the sigma notation, when you have a sum of the sigma notation from a sum of terms, you can distribute the sigma to each of them. So that means you have sigma I from 1 to n taking on the f of s by, right, times this, and then plus what? Sigma I to n taking on the j of s by times this. Then when you have the limit of a sum to, it's also what? The sum of the limits, right? So that just gives us the limit as n approaches infinity of this first piece. and then plus or the limit as n approaches infinity of this second piece. And each of these are definite integrals. So we get this. That's why we have that. Right. Yeah. And as I said, you just need to see how this works. I'm not going to test you on these proofs. Now, the next one is if you have a difference, but for the difference, you can just see the difference to be a sum, right? And then use the constant multiple rule to bring it out. So that is proven based on this, but we are not going to go through. If you're interested, you can still use this limit of sums to show the difference one, right? So it is like plus or minus. Okay, so now let's do this last example and we call it a day. So use the properties of integrals to evaluate this, right? So that's example 6. Let me do this and then I'm done. Example 6. As I told you, 5.2 is the longest. It's like 50 slides, a lot of ideas on this section. Okay, so now let's do this. Let's use the properties we just learned. Now for the first bit, I say, okay, now for this first part, I see, okay, a sum, a definite integral. So that'll be this dx plus this 3x squared dx. First step. The next thing is, oh, I'm doing a definite integral of a constant. The integrand is a constant. So that just be 4, 1 minus 0 is the area of a rectangle. Plus for this piece. Now for this piece, I have a constant which doesn't depend on x. So I can pull out 3, 0 to 1 s squared dx. And then there's just 4 plus. Now for this other piece, we did this in 5.1. From 5.1. This is 1 over 3, right? So that means that we have 1 over 3. Later on, we learn efficient ways to do this. We don't have to reference stuff. Yeah, so we move on to other stuff. So that's 4 plus 1, which is 5. So that's it. Okay, thank you so much for sparing some time for me to wrap this up. And next time we meet, we'll talk a little more. We'll still be on 5.2. This one is the longest, but 5.3 will be quite short, and the 5.4, 5.5. Yeah, so that's it for today. Thank you for your time. If you have any questions, feel free to reach out. So all the best. Enjoy the rest of your day. See you on Wednesday. You are welcome, guys. You are welcome.